basically, we said already like that we need to find gradient descent methods that help us find the optimal solution for like all sorts of kind of complex discriminant functions, and we said already that it often is impossible to find like an analytic solution to this problem, and we need to find the optimal parameters so that the discriminant basically finds an optimal, like the minimal error or the minimal cost, or the minimal error criterion that so we need to find the parameters that minimize the error criterion, whatever that is, or cost criterion that and basically we can define this as like we want to find W star, which is the optimal set of weights that produces the minimum of this error given a certain x, and this capital X here, so that means given a certain training set. Okay, so this is an entire data set instead of just like one input vector. And in order to do this, we utilize a iterative process which is called gradient descent. And basically what this gradient descent tries to do is, if you have like an error function that lives in like a high dimensional space, which is dimensional with respect to like the weights that we have. So each set of weights and the discriminant produce a certain error, right? And if you plot all of these weights in, let's say, if you have two weights, you can plot that in a three-dimensional space, and like that would look like a surface, maybe like a mountain range or something like that in that three-dimensional space. And what you want to find is a way from the top of the mountain peak down to the valley, right? Because at the valley you have the lowest level of error. And we're gonna look at that in a second. But basically, what the gradient gives you for each of these weight parameters is the steepness of the error at a certain point, right? And if you would actually walk up the hill with the gradient, you would increase the error. But if you walk down the hill, which is negative gradient, then you walk down the hill. And you walk down the hill with this minus here, so you basically take the error function and you derive, make the partial derivatives for each of these wi's. Okay, so you don't do it for the entire weight vector at once. You do it for each wi, so each item in the weight vector separately, so that's why it's like the partial derivative. And you walk down with this minus, and you walk down with a certain rate. So you basically have to define this eta value, which is the learning rate. And you can already imagine that this is an important parameter. It shouldn't be too small, because then you would make minimal updates all the time, and it shouldn't be too large, because then you jump around in the error space all the time. Okay. And then what you do is you take this negative gradient step, so to say, this delta wi, which is defined through this partial derivative, and you add that. So you have a minus here, and you add it so that you subtract it here, right? You add that to your old weight, and your new updated weight will be just that sum. And then you do this again. So you reiterate, iterate through this all the time. All right? So very important, this eta value is crucial. Like you have to like find a good one, and this is another hyperparameter that needs to be validated. And sometimes, if you have complex learning and very large data sets, you don't just stick to one eta. In the beginning, you want to make maybe big jumps, and then towards the end, you want to make smaller jumps, because you kind of have found already like a good spot where the error is low, and you just want to find, like, fine-tune where is the optimal location. Okay. All right. So choice of eta is crucial, and changes efficiency and precision. If the gradient is 0, we have learned, or we have found an optimum. So this is basically what happens. So this is this mountain range. Basically here you have your criterion on this dimension, which is error. Like this is like it's 3 or -3 or whatever. And you want to get to the lowest value. And here you have your two parameters, θ1 and θ0. And if you change those across the entire thing, you change the amount of error you make. Okay. And this is only visualizable if you have two parameters, obviously. But if you have like 100,000 parameters, like this curve is kind of difficult to visualize, but it still holds that you want to walk in the negative direction. So if you start randomly, you set both to 0.5 or something like that, and then you basically compute the gradient here, so it gives you like this kind of like plane here for the gradient. And you would walk for both separately, for θ0 and θ1, you walk in the negative gradient direction. And this is basically this direction, which goes down the hill. And the distance of like how much I walk here is dependent on the eta value. Okay, so if the eta is very small, I would like walk minimal steps like this. And if it's too large, or if it's very large, I can walk from here to here, etc. But what you can already imagine is, let's say, I don't know, if you're kind of there, for example, and your eta is too large, so the direction of the gradient is going down that hill, you can, for example, jump over on that side. So you can basically, like, if the eta is too large, you can jump over the valleys. So we'll visualize that better later on. Okay, so this looks like it could be the optimal value down here, the global optimum, but these methods don't guarantee you to find the global optimum, okay? So if you start here, this is what you'll find, right? And that's a local optimum. You're not going to get out of this anymore because the gradient's going to be 0, and like with a 0 and I multiply that with some value and I add it to something, it's not going to change the weights anymore. So if you're down here, you're stuck, okay? What can you imagine could help you not get stuck with local optimum?
Random points to start.
Sorry?
Picking random points to start.
Exactly. So you randomize your start points and you find, like, you choose 10 start points or whatever, and you choose the one that gave you the best result, okay? So that would be one way. So you just train it 10 times or whatever, and you choose the one that resulted optimally. So if you start here, you end up there. If you start here, you end up here, okay? And if you, I guess, start here, you would end up here. So this is one way. And there are, so for example, what you just said, like, kind of like genetic algorithms where you would like have a whole population of algorithms that try out to go down that like a whole set of paths, and you want to find the optimal one through that process. Okay, is that clear more or less? All right, cool. So, and this kind of also visualizes that. I think I found that somewhere like on GitHub. It's kind of cool, where basically says if you start here, you end up there. If you start here, you end up here. Okay. So this is kind of just to summarize this. Let's do an example for this, and it's basically, the example is logistic discrimination. So instead of a linear function to discriminate between points, so we're not learning like a line, straight line through the space. We're learning like a sigmoidal function, which are these functions here, right? And this one's the Fermi function. I think that's what we call it. And basically, these weights here and this weight, so these weights define the steepness of this thing. You can have this like this, you can have it very steep, or you can have it very flat, right? So, and then the W0 is kind of like tells you where to locate it on the dimension, okay? So if you go forward or backwards, so if this parameter is 0 here, the curve goes through 0 with like it starts at 0 and it would go through 0 at 0.5, okay, if that was 0. And then you can change the steepness, but it would always go through that point with 0.5. Okay. Basically, this is a Bernoulli distribution, but it's not very important in this case. So you can imagine like we're evaluating a coin toss problem, for example. And our error that we define here is the cross entropy. And in this case, the cross entropy is what we predict, or like we want to minimize the entropy between what we predict and what's the target. Okay, so that's like what it actually is, and that's what we predict. We want to minimize that, okay? And this is just one error function that we can define. And the cool thing about this error function is the partial derivative of it is not very difficult. Okay, I mean all these logs, but they're falling away if you derive it. Okay, so we need to calculate the partial derivative, and we know that y equals a sigmoidal. So this is our discriminant hypothesis space, so to say. And if we take the derivative for this for a, we end up with this. Okay, so very simple partial derivative. Does that make sense? So just we just have to keep that in mind. That's one of the ones that we're going to use. So what we're going to do now is we take this cross entropy function, right? That's dependent on a whole set of w's and a w0, and we want to take the partial derivatives. So we first of all calculate this delta, this weight update step for each wj. These are in here, right? And so we take the partial derivative for each of them, and this is going to be the same for all j's, right? And so again, like we have this eta here, and we have to derive this now, so the logs become the 1 divided by, right? So if you take the partial derivative of a log, you just put them underneath, so 1 divided by, and then you have this with chain rule there, and basically you can simplify this down to this function here, because here you have this multiplied in, you have this, and in the end you just have rt minus yt times x. Okay? So this is the updates for the weights in the sigmoidal part that is here, where you calculate this dot product between the input vector and the weights. Okay? So you have as many of these weights as you have input dimensions. Okay? So you have d input dimensions, so you have d many times this function, but it's always the same, right? And then for w0, well, w0 is this value here, so all these values fall away, so you have 1 divided by 1 plus exponent minus a, exactly because this is w0 here, so you have just this. Okay? So this boils down to that part, so no x needs to be multiplied in here anymore. So this, because this this dimension is not dependent on the x, right? So if I do a partial derivative to this variable and not to these here, this x falls away because all of these will be 0, right? And so our update functions are now, there should be a delta, maybe not, that's fine. So the new weight will be the old weight plus eta times this. There was a minus somewhere here, I think. Yeah, also the minus falls away. Yeah, okay. And then it's that for W0. Okay? And so this would actually allow you to formulate an algorithm to do logistic discrimination. And this is actually what happens in here. So you have two classes here, ones and zeros, and you try to fit this curve in a way that basically, so you randomize your weights. They're randomized between minus 0.01 and plus 0.01, and you repeat just this whole loop here where first you set your delta j's to 0, and then for each dimension you update the weights here, and you calculate. So basically, this is the predicted output that you're producing right now, and this is the update function for each of the weights. And is there like the so you have a 0 dimension as well. So that's like the W0 is the one dimension, like the the one that gives you the location. Okay. And then so this is how you compute the update, and this is when you apply the update. Okay, makes sense? And so you can visualize this nicely, where basically the more you train, the better fit will be of the sigmoid with those lines. Okay. So that's that for this part. I should have some neural networks somewhere. And it's a little bit of a change of pace with neural networks, because before we go into the two difficult parts of neural networks, and we're going to talk about multi-layer perceptrons and like how all these networks can be trained. I'd like to just basically give a little bit of a motivation of like how these neural networks came about. And this is my half-truth, so to say, or like dangerous presentation about biological neural networks and the brain, so to say. Brain, super complicated, kilo, and I'd like to give like a sort of like a computer versus brain kind of juxtaposition first. So computers have few but complex processors. So each computer, usually like in the 90s or early 2000s, had one processor. Now we have clusters that might have like 10,000, 20,000, 30,000 processors. Each of those processors are low connected, but they're super complex, right? They can do floating points and so on. They have a lot of memory, and so on, but they're not connected very well. So they're like the connectivity between those is pretty small. Like if you think about like the network at USC, there might be, I don't know how many computers, but all of them are just connected through to a few of them. However, they process information really, really fast with gigahertz, so they're like millions or trillions of operations a second, so that's very quickly, but they are very intolerant towards error. Like just a few spikes in the electricity or whatever can cause them to have a problem in their computation, and often errors or these mistakes are fatal and could lead to a total stop. So like that's when, you know, blue screens happen and stuff like that. Okay, and you program them through explicit writing of like code. So you sit down, you start your Python script, and you write explicit commands to the computer, right? And these commands are completely separated from your data, right? So you have your program, you have your instructions, and on the other side you have the input data and the data that you're processing, okay? And yet, as you can imagine, like the other side is going to be the brain. It's going to be complete opposite for all of these points. Loads of processors, 10 to the power of 11, many neurons in the brain, but they are not very complex. They have one output, they collect information from a bunch of inputs, and they produce zeros and ones, so to say. Like they spike or they don't spike, okay? They have super high connectivity, so each of these neurons is connected to many, many neurons, maybe 100,000 even, right? But their frequency is very low, so they can maybe do a few hundred spikes per second. So their spiking is in the hertz, or like 100 hertz or something. However, they're very high, like tolerant to mistakes. So there is an enormous amount of redundancy in the brain. If one neuron doesn't fire anymore because it, I don't know, like died or something, you're not stopping to work, right? Like errors only cause partial failure. You're not going to forget an entire lecture just because you got hit in the head and stuff like that, okay? And the interesting part now is that there is no explicit programming. Nobody goes in there and like fiddles around with the neurons to change the program. So we learn through examples, through experience, through rewards that we get. So we, I don't know, we learn how to catch a fish by trying to fish, and then we get a reward because we can eat the fish. Okay, so this is kind of like this evolutionary learning or programming process. And I think one of the coolest things, and this is really where deep neural networks are excelling at and give us so much more power than shallow networks, is that there is no separation between data and program. So everything that is stored in the brain and everything that basically makes decisions and produces outputs is stored the same way. So you have connections in the brain that store memory, that store information, and produce like actions and commands and so the program and the data are not distinguishable anymore. They're just weights and connections in the brain. Okay, and this is actually like how you can build neural networks or neural associative memories, where, for example, you can store information in a neural network, and you can retrieve it by giving a certain key as an input, and it produces an output. Okay, so that's kind of like where the program and the data are not distinguishable anymore. This is just an image of like how the brain looks like. So frontal lobe, lots of personality, temporal lobe. You have like acoustic processing, occipital lobe. You have the visual processing. So you have the primary visual cortex back here. You have auditory and cortex, and you have here the motor cortex and the somatosensory cortex, which is interesting because this is where you produce the commands for your limbs to move and to like produce speech, etc. And here you feel, and I really love this representation here because that gives you an idea on the somatosensory. So this is the perception part, like how the number of neurons is distributed across your body. So for feeling, your head is really, really large, and in particular, like your lips are very large in this homunculus. That means that there are many, like out of the entire availability of the neurons, a lot of them are allocated for very small parts of your body. So the lips get a very large allocation of neurons because it's so important for us to feel with the lips or the tongue, for example, or the fingers. And so your hands and your fingers are very, very sensitive. In contrast, your back or your hips are very, very tiny pieces in this, even though they're large parts of your body. Okay, so this kind of just gives an idea of how many neurons are associated or how many neurons are allocated for certain body parts. The same happens for the motor strip, where it's even more dominant. That like the hands are incredibly powerful, and like you can move so many, like you can produce such intricate behaviors with hands that and there are many muscles and joints that need to be controlled. So you have a lot of processing power, a lot of program, a lot of data that is required to move your hands. The same for lips and tongue, where the production of speech is influenced, and as you can imagine, speech production is very complex, and we need to be really like precise about production so that we understand each other and so on. So there's like a lot of processing going into language production. Just also as like kind of like a motivation why there are layers of neural networks, or like multiple layers of neural networks, like deep neural networks and so on. There are also layers in the human brain. So this is from the cortex, cerebral cortex, where there even seem to be like these strata of connectivities where neurons that are on the top are connected very closely to each other, and then you have neurons that are connected here, so they are connected across, so they are like basically recurrent connections where you have connections in one layer towards each other, but then you also have these connections that go up and down, so these are connections that go through multiple layers, okay? And then you have a wild, strong connectivity at the bottom of the cerebral cortex. So this is just kind of like, it's about the organization of neural networks, okay? And the brain itself. Each of those neurons here has its dendrites and an axon that it connects to. So in the dendrites, and we're going to visualize that here. Basically, the dendrites are all before the soma, or the center of the neuron, and basically the dendrites are the tree where it gathers information from other neurons. Okay, so this is in the dendrites is where the neuron is connected to other neurons. Okay, so this is the red neuron. It's connected to the orange neurons here, there. So these are the synapses are basically these points of interaction between two neurons. And what the neuron now does is it gathers all this information from outside and it processes it in the center and decides if the neuron is shooting information along the axon or not. And then at the end, this axon splits up again and connects to other dendrites of other neurons. This is kind of important because we're going to motivate the artificial neural networks based off of like this model, okay? And does anybody know what the myelin sheath are?
It helps with auditory conduction.
Yeah, and then it basically insulates the signal so it can shoot it faster. So it's kind of fun. And yeah, so this is basically where the information is gathered and the action potential is shot along. So what's also important is that the neuron does a spatiotemporal integration. So it integrates information over space, so from other neurons, right? But it also doesn't do that just like on an instantaneous basis. It gathers information over time, okay? So it has this integration over time and space. And yeah, that's also like going to be motivating for the artificial neural networks and how they will look like. So information is transmitted when a neuron fires, and then the connections between neurons will be are synapses, but there's a important distinction here. Some of the synapses are excitatory, they excite the other neuron, and some connections are inhibitory, they like suppress the other neuron, okay? And this is again very important for the artificial neural network because how would we express these connections between excitatory and inhibitory neurons towards each other? Well, we have weights and we have real numbers, so excitatory greater than 0 weights, inhibitory less than 0 weights, okay? So that's kind of like how we will model this difference here. If a certain threshold is met, an action potential is sent. We don't necessarily work with that all the time, so we, if we would produce these spikes, we would have like issue with modeling and processing time. It's not very easy to like simulate these spikes because there are like discrete events in the world, so we would have to synchronize between artificial neurons. So what we do is we modify these excitatory neural networks into rate-based neural networks. So instead of like simulating every single spike, we simulate the rate of spiking. So we would say the neuron is firing at 100% ability, that would be an output of 1. The neuron is not firing at all, it's a 0, and if something between, like half rate, it would be at 0.5, 3/4 rate, it would be 0.75, and so on. Okay, so we produce values between 0 and 1, which are rate-based firing values. So it's not, like we're not simulating every single spike, but we're simulating a rate of spikes. Okay, and this will become more clear when we see it in the formulas. And just basic biology, so the action potential is a positive electric charge. Is not like normal electricity that comes out of the plugs. It's ions rather than electrons that move, and basically this is how this looks like. This is a spike, or basically the action potential of one neuron, and we start with a negative like resting load, and through integration over time, this this action potential might go over a threshold, and then this is when the neuron decides to fire, and it then retracts in the action potential. It actually goes below the resting potential and basically goes to the resting potential again, and that basically just means that a neuron cannot fire infinitely many times. So this going under the resting potential basically just means that a neuron has to like rest before it can go back. And what is happening is like there are different channels where ions are either outside of the neural membrane or inside the neural membrane. That, like, the location of these ions on either side defines the electric load of a neuron. Okay, I don't want to go into too much details, but basically these are the typical phases that you can see here, and with the different types of channels. In this case, we're just visualizing the potassium and the sodium channels, yeah, and so some of the reasons why they can't fire at infinite rates is like there's actual active involvement in pumping those ions to certain levels of electric charge, yeah, so this is kind of like just a few, it's not that important, but it's a nice motivation. So anyways, this action potential now gets sent along the axon, and at the end of the axon there are synapses where the connection or the information gets transmitted from this neuron to the next neuron. This is just also a summary of how this looks like. And yeah, so the first couple of like artificial neural networks that were invented really tried to go very, very deep down into modeling every single channel separately, and this is the Hodgkin-Huxley model that basically modeled both the sodium and the potassium channels, as well as like a leakage channel where basically some ions just fall out and stuff. And you can compute this very complex, and their model was derived from the giant octopus axon, which apparently you can like just see without any visual aids. You don't need a microscope or anything. You can just use it. They modeled both sodium and potassium channels as well as a leakage channel, and it's super complex. I could show you all the derivation functions and the function model, and you will immediately see that it is not very useful to like learn larger networks with these kind of models. So these are way too complex to actually learn complex neural network models with. Okay, so what happens basically is we need to reduce the complexity, and one way to reduce the complexity was to move away from these spike-driven or action potential-driven neural networks to a rate-based model, and this is the basic rate-based model derivative function that we are often using. And basically what this means is, so our membrane potential, so this is the charge of the neuron itself, is dependent on the old potential, okay, plus some external input. So this is like whatever the sensors, like the eyes, for example, neurons in the eye get light input or acoustic input, or something else like feeling, touch, etc. So this is external input. So X again is our the input that we will give to the neural network. That could be our data, and then we do a spatiotemporal integration over the connections of the other neurons. So these are our weights, the C weights, and Y is the output of another neuron. So in this case we are modeling neuron J, and this is from neuron I, okay? And this is the output of neuron I at a different time. So this is time t minus dij, and dij just models like the time it takes from the information from the neuron I to come to neuron J. And then these C parameters could be positive or negative, and they give us excitatory or inhibitory connections between those neurons, okay? So, so we compute the membrane potential, and then to the membrane potential we now apply a certain output function, and we call that a transfer function. So basically, the output of the neuron is based on the membrane potential, okay? And this function here could be any of these functions. It could be, there are many more functions. And there are certain reasons why we chose these, or why we choose these, and we'll get to that probably next week. But there are many reasons for that. So first, the easiest one is f of x is x, so that's a linear transfer function, so we don't do anything. We can have this Fermi function that we had before in the logistic discrimination, that is like a valid version, or like a valid use. And is this that one? No, it's not. It would be at 0. So this one is actually tangent hyperbolicus. So that's also a valid one. So that goes from -1 to 1. And so we have a whole set of these functions. We can use any of them. So what is important is that basically this neuron, the current state of the neuron, or the update, the next state of the neuron is dependent, or depends on the old state, the old membrane potential, plus the external input, okay? So, and the external input comes from the outside world, and it comes from other neurons, because that's very important. So, let's say, for example, we remove this external input, right? So now we have a neuron that's only dependent on the previous input, right? So, and we take the derivative here. So uj equals minus uj. So what are typical functions for this? So how do we receive this as a derivative? Well, so a function that's when you take the derivative and stays the function, which one is that? That's the exponential function, right? Like if you take a derivative of the exponential function, you have the exponential function. And how do you get a minus? Well, you have a minus in the exponent, right? So that's how you end up with a minus here. So like often these, like the membrane update functions, they are exponential and they fall exponentially. That means like when no external input comes into the neuron, it shouldn't go up with membrane potential, right? It should go down. It should go down quickly. So that's important because if this is not the case here, then we would have like exploding excitations within the neural network. Okay. And then what happens if this is gone here? Like there's no U here. Then you have a network that's, or like a neuron, which the membrane potential is only dependent on external input. What is the difference between that and a neuron that has this value?
Memory?
Exactly. So the neuron that has this value of the past knows what it did last time, but the one that doesn't have this term doesn't know anything. Like it always does one decision at a time. And the cool thing is, we never model this. So it's like in the beginning, we start off with not having these. So we have like perceptrons and neural networks that learn one step at a time. But then with deep learning and long short-term memory neural networks, we will have like neurons that know what they did the last time. So they can learn dynamics, they can learn things about the past. All right, I think this is a good point to stop, and I have to run to the bus to get to ICT. But are there questions for this? We're going to continue with this on Wednesday.
So, quick question.
How does this one like differ from the linear regression we just talked about? Like, can we just treat that as a function to compute the weight of computing?
Yeah. And we're actually going to come to that. And so there's going to be the easiest neurons that we're going to learn are so-called perceptrons, and they will exactly do linear discriminant. So they learn where to split the space into two halves. That is exactly true. And then, but the cool thing about this one is that it allows you, through this external input where information comes from other neurons to it, it can learn it can combine multiple of these linear discriminants. And so if you combine many discriminants together, you can learn more complex functions. And we will learn that if you combine these neurons in a multi-layer fashion, like we have multiple layers of these neurons working together, you can learn any function with any precision you want, if the function is continuous and not jumping around too much. Okay? So yeah, neural networks are cool. Yeah, it's not that tragic. You were traveling, right? Yeah. That's okay. We can give you like an example on that one, and then you just yours next to this.
So annoying.
This is just for the homework.
Oh, hold on, okay, I got it.
You never mentioned any.
Oh, right. Where did you put it in there?
This part I'm not able to do.
I mean, you're like
Oh, okay. This is just for the linear processing class.
oh, you're,
Yeah.
oh, your class, oh, I see. Oh, let me get this up. That's your class.